So we're still on the topic of putting molecules together. We're on a tie-breaking strategy, okay, using formal charge. This is very similar to oxidation numbers that you'll use in grade 12 chemistry. Okay? So it's a good skill to start learning in grade 11 because all Chem 30s have to do this in grade 12. Okay? So Lewis structures based on Lewis dot diagrams are fundamentally built on s and p orbitals. There's lots of sort of exceptions or places where the steps don't lead to perfect results. Okay? If we get two structures like you can from thiocyanate, we're going to figure out whether one is better using this formal charge. We're going to look at how many electrons we've assigned around an atom and compare that to how many valence electrons it has. Okay? If something only has 4 valence electrons and we end up starting to assign 6 or 7 around it, that's not very likely that all those extra electrons are going to come in. Okay? So the structure with big differences between how many valence electrons it has and how many we put around it are going to be unlikely. Okay? The most probable structure would have, if carbon has 4 valence and we assign 4 around it, that's very likely. So I'm going to start with a repeat of the steps to put an ion together. If you had thiocyanate on an exam, you'd realize that has a charge. You can't use bonding capacity. You're going to count the electrons, connect things together, start on the outside with an octet, and work your way in. So I'm going to start by counting electrons, including factoring in the charge. So sulfur is in group 6, carbon is in group 4, nitrogen is in group 5. Each group tells us how many valence electrons it has, and then it has a -1 charge, so I'm going to add 1 electron to factor in the charge. So I have 6 and 4 and 5 and 1 is 16 electrons. 16 valence electrons to put into the structure. Now the way that molecular ions are written are often a hint towards the structure. So it's written SCN because that's the order the atoms come in. And it does match the highest bonding capacity in the middle, which would be your guide if you weren't sure. So I've used up 4 electrons already, putting in 2 dashes. We have a whole bunch left. We're going to start on the outside with octets. The sulfur only has 2 electrons around it. That dash, 3, 4, 5, 6, 7, 8. And I've used up 10 of the electrons so far. I'm going to go to the nitrogen. We don't deal with the middle at this point. We stick to the outsides. Nitrogen has a dash, so 2, 3, 4, 5, 6, 7, 8. So I got octets on the outsides. I have 6 dots and 6 dots, which is 12, 13, 14, 15, 16. I've run out of electrons. I have no more to assign to the middle. So then you'd start pulling outside electrons, lone pairs in to make octets in the middle. Okay. Carbon is short 4 electrons. Okay. So I'm going to go through 2 possibilities. There's actually more, but we're just going to compare 2. Okay. I could pull from both sides. Okay. I could pull those in, and then I could pull in from the other side. So carbon has 4 electrons to begin with. I could pull from the sulfur 5, 6, and then from the nitrogen 7, 8, and get an octet. But that's not the only option. I could have just pulled everything from the sulfur. Okay? The other option, I could pull those, but then I could have went to the same side, okay, and pulled another 2. That would also pull 8 total electrons around carbon. And we're going to compare those 2 options, the green option and the red. So I'll do the green option first. sulfur, carbon, nitrogen. Okay, I'll put the dots in last. So here's where I'm pulling from the left and the right. So I pull from the left, I get a double. I pull from the right, I get a double. That follows all of our rules. Or I could have tried the red version, which also follows our rules. And now the red bottom version would make a second bond, and then the top red pull of lone pairs into bonding pairs would triple up that side. And both of these have octets around all the atoms, but one of them is more favored than the other. So we're about to look at formal charge. We're going to compare, I'm going to use some short forms, the valence electrons to how many actual electrons we've put around it. If the valence and the electrons we put around it are the same, then it has no formal charge. If we put an extra electron around it, it'd be -1. If we're short an electron, the formal charge would be +1. Okay, electrons are negative, so if you have extra electrons, it's negative. If you have a deficiency in electrons, it's positive. So those valence electrons, it's the same numbers that are just hidden above the screen that we use to count our electrons. Sulfur's in group 6, so 6 electrons. Carbon's in group 4, so 4 valence. Nitrogen's in group 5. And I'll repeat those numbers when I look at the second structure. Okay. Now we're going to count how many electrons are around the atom. Now, we have to, how does formal charge deal with those bonds? So we've got a dash, and the dash is a pair of shared electrons. With the dashes, with formal charge, you're kind of going to just split them up and send 1 electron each way. Okay, there's 2 electrons, they each came from, 1 electron in the dash came from sulfur, 1 came from carbon, we're just going to put them back. So our sulfur has 2 lone pairs, 1, 2, 3, 4 electrons, 5, 6 when you count 1 electron from each of the dashes. So sulfur, we've assigned 6 electrons around it. Okay? The lone pairs are entirely on the sulfur. The bonding pairs are kind of half each way. Carbon, we've got 4 bonds. We're going to count 1 electron from each of those 4 bonds. Nitrogen has 2 lone pairs, 1, 2, 3, 4, plus 1 from each of the bonds, 1, 2, 3, 4, 5, 6. So now I can do my formal charge. What's the difference between the electrons that it started with valence to how many we've assigned? Sulfur has 6 valence, we've assigned it 6, so there's no extra or deficiency, 0 formal charge. So that's a stable sign of the structure. Carbon is the same thing. 4 valence, we've assigned it 4. It has a formal charge of 0. Nitrogen had 5, but we've assigned it 6. We've assigned it 1 extra. So it's got an extra electron, so it's got a -1 formal charge. Okay. Now the formal charge should always add up to the charge of the molecule. Our molecular ion is -1, and we have 0, 0, -1, so good. Our formal charge adds up to that charge. Okay. Essentially, what in this structure, we're saying the extra electron that made it -1 went to the nitrogen atom. That's where that extra electron went. Okay. Let's look at our other structure. So the bottom is our actual. Sulfur has 2 electrons, 1 lone pair, and then a 3rd, a 4th, and a 5th. Carbon has 4 bonds, 1, 2, 3, 4 bonds around it, so 1 electron from each, no formal charge there. Nitrogen has 6 dots, 6 electrons, and 1 bond, so a 7th electron around it. So our formal charges, sulfur is short 1, has 6 valence. We've only put 5 around it. It's short 1, so it's got a +1 formal charge. Carbon 4 and 4, so that matches, no extra, no deficiency. Nitrogen, it has 2 extra electrons, so -2 for the 2 extra electrons. So how are we supposed to use this? To determine the most plausible Lewis structure between 2 or more options, the one with the lowest total formal charge is most likely. So 0, 0, -1 has way less formal charge than +2, or sorry, -2 and a +1. There's more formal charges here. Okay? You know, here we're 1 off. Okay? If you kind of add up the absolute values. Here we're at a 3 count if you add up the absolute values. Okay? So the 1 count is the most likely. So we would predict this as our most likely structure using formal charge. Now, if you see a couple other options, yes, there are some other possible options that I didn't do. I just did 2. So last, to finish this off, and I want you to think and help me a little bit. What else do I need to do a proper Lewis structure for this? Yeah, we need square brackets, and then we put the charge on the outside. I didn't want to include this while I was working because that's just going to clutter everything up. So I like to do formal charge, figure out the most likely structure, and then complete it. So predicting these structures is something any Chem 20 would do. AP should be able to tell me which one's more likely. So it's just a slight extension off what everybody needs to know. So that's formal charge done. Next is going to be resonance, and this is when the 2 options are a tie for the difference. They're both equally likely, and the truth is actually the average of the 2. And that is resonance, averaging out a couple structures. So when 2 or more Lewis structures are required to correctly convey the bonding in a molecule, so that'd be the formal charge is the same in both. Okay. We call those multiple structures resonance structures. The molecule is best thought of as neither drawing, but the average of the 2. So you might think the molecule would flip-flop between the 2 drawings, but that's not what we see with experimental evidence. We do not see a flip-flopping. We see an average. If you get a 70 on a test and a 90 on a test, you are best thought of as an 80 student, not a 90-70, 90-70, 90-70 flipping flop back and forth. We're going to look at carbonate that we've looked at already, and benzene that we haven't looked at, but it's super important for grade 12 chemistry, so I want to kind of prepare you for that ahead of time. So I'm going to start with carbonate with its resonance structures. I'm not going to go through all the steps to draw out carbonate. It's in your notes already. It's in a previous lesson. I would have counted all the electrons, put carbon in the middle, the oxygen's on the outside, and we ended up pulling 1 pair of electrons from the outside in. And I just chose to do one of the structures when I did this previously. So I'm kind of going to jump back quickly to where I would have left off. Okay. So I chose in the previous example to pull a lone pair from the bottom left and pull and make a bonding pair on that bottom left. But it would be equally likely, the formal charge would be identical if I'd done it from the, instead of the bottom left, if I did it on the bottom right. And it would be equally valid if I'd done it from the top. If I'd pulled a lone pair from the top and made the double there. And because they're all equally valid, same formal charge everywhere, octets everywhere. All three of these we call resonance structures. The best way to think of carbonate is the average of all of these. Now, how resonance structures are often drawn is we square bracket the whole thing, whether they have a charge or not, and just put a plus in between. We're going to talk about what type of bonding we actually see. Okay. So what we don't see is for 2/3 of the time the top has a single, and then magically 1/3 of the time we see a double. Okay? We see an average. So I'm going to color code one of those bonds so it's clear to talk about them. I'm going to color code the top. So the top bonds are now all purple. We're going to average out those purple bonds. Okay? How do you take any average? Okay? Well, you add everything up and you divide by how many things you have. Okay? If you have a 70 and a 90, you add them up and you divide by 2. Okay? We're going to do the same thing. How many bonds do we have? And then we're going to divide it by 3 because there's 3 structures. That's the type of bonding strength and length that we see. So in the 3 structures, it's going to clean up my drawing a little bit. It kind of looks like there's a double there. We have a single in the first, a single in the second, a double in the third. It's 1, 2, 3, 4. In total, there's 4 bonds spread out over 3 structures. So on average, we have a bond and a third. And I could have done that same math on the bottom left or the bottom right. Everywhere we end up getting 1 1/3 of a bond. And that's what we see in terms of the bond energy and the bond length. We see a bond and a third length and strength. So it'd be a little bit shorter than if we just had a carbon-oxygen single bond. Okay? The more bonds you have between atoms, the closer they get together. That was one of our case studies with the single, the double, and the triple. Okay? So we don't see any double bonds in the actual structure of carbonate. We see the average. Okay? In grade 12, when you study organic chemistry, you'll look at benzene, and there's only 2 structures for benzene. It is a 6-membered ring. Every carbon has a hydrogen. Okay. Straight up bonding capacity is going to work to put benzene together. We don't have to count up all the electrons. We just have to get 4 bonds everywhere. Okay. Elements in the first and second period follow bonding capacity all the time. No, I'm not done. That doesn't work. If you count the carbons, there's only 3 bonds so far. We need another bond. One way to solve this is if you put a double bond there. The carbons on both sides will have 4 bonds now. I can't put a double in the next spot because I would put 5 bonds on the top carbon. But if I go double, single, and then double again, I fix those 2. And then if I go single and then double, it fixes the bottom two or the last two carbons. And now everything either has a duet if it's hydrogen or an octet if it's carbon. But we don't see double, single, double, single, double, single when you study benzene. Okay. The reason for that is this drawing is one of two equally valid drawings. I could have put the double on the top right instead of the top left, and it's equally valid. So that's what I'm going to draw out as the second resonance structure. So I'm going to put singles to start all around the circle. I'm going to put in my one hydrogen at every carbon. And now instead of top left for the double, I'm going to go top right. It works just as well. Double, single, double, single, double. These are the two resonance structures for benzene. One of the outcomes in grade 12, not grade 11, in grade 12, is that you know that benzene has 0 double bonds. The bonds in benzene, we're going to do that same averaging. I'm just going to put an arrow instead of color coding. I'm going to look at the top left where I put those blue arrows. What's the average bond length and strength that we see? We've got two structures, and we've got 1, 2, 3 bonds between the two structures. Benzene, you see a bond and a half all the way around. Okay? If you do the same math on the left-hand side where I put the green arrows, you get a bond and a half again. We see a bond and a half all the way around. We see the same bond length all the way around benzene. Being able to draw this, a Chem 20 should be able to do. Okay? Doing this resonance is 20 AP or regular 30. Would have to realize this. Okay? Your Chem 30 teacher will draw those two structures of benzene and say they're equally likely, and the truth is the average. Okay. So the octet rule is a pretty huge guide for us. Again, it's not perfect. It assumes there's just s and p orbitals. I want to repeat that incomplete octet that we could get in group 2A and 3A. Or just straight up group 2 and 3. You need to watch for these on exams. Okay. Group 2A, most likely boron, and 3, beryllium. They do not have enough electrons to make octets. That's why we tend to see incomplete octets with these atoms. So, and I just flip them. Now they're in the right order. Beryllium is group 2, boron is group 3. Beryllium in group 2 has 2 valence electrons and 2 empty orbitals. Now we don't normally write those empty boxes, I'm just emphasizing them. So we see examples with beryllium with 2 bonds. Where we're going with this next is shapes. So beryllium dihydride tends to be straight. There's no lone pairs in this structure. Because of the incomplete octet, there's no lone pairs to bend it, to repel each other. You've got to realize that the beryllium doesn't have 8 electrons. You need to not do this. I'm going to erase it. Don't just start making up electrons and making up an octet around it. There just isn't enough electrons to do that. I've got to take those dots out. And we get the exact same thing with boron. 3 valence electrons. It's got an empty orbital. And we see boron bonding with 3 things that have a bonding capacity of 1. I'll use the same 3 H's that I used in my previous example. There is no lone pair there, so the H's nicely, evenly spread themselves out. You could guess the bond angle when they evenly spread themselves out, and we'll talk about that bond angle in the next lesson and what name of shape we have here. Okay. If you think there's an octet and you think there's a lone pair, you'll have the wrong bond angles and you'll have the wrong shape. So that's incomplete octets. We can have expanded octets. Okay, we saw sulfur hexafluoride already in our notes. You don't see this in period 2, but beyond period 2, we've got those d orbitals that we've been ignoring, but they can bond. Lewis theory ignores them. You would have to use the 5 steps to predict these structures. Okay? Any Chem 20 could get the first 2 and be asked to draw them. When you go through all the steps, there ends up being no lone pairs on sulfur, and the 6 apps just all have single bonds. I did not put my lone pairs into that. I'm just doing a straight up structural diagram. So that's what every 20 has to do. In AP, we'll talk about what orbitals were needed to make those 6 bonds. Starting at S, then P, then D. 1, 3, 5 is the count of those orbitals. So we need 6 orbitals. So we're going to use up one S. We can't use a second S because there isn't a second S. Okay. We didn't get to 6 yet. So we're going to need 5 more. Well, the P's can only give us 3 of the 5. Okay. Now we got 4 orbitals. Okay. We need 2 more to make the 5th and the 6th bonds. So we're going to go to D's, and we only need 2 of the 5 D's. 1 S, 3 P's, 2 D's is 6 orbitals. That would make our 6 bonds. Okay. Anybody in Chem 20 should be able to put together the second structure. Okay. And you don't get any lone pairs again. The 5 F's surround it. Okay. And I didn't put my 3 pairs of electrons. I'm just doing a straight up structural formula. So that's what everybody in grade 11 can do. We've got the extra, what is the orbitals that we needed to make this. Okay, there's more than 4 bonds, so you need at least 1 D to do it. So we need 5, there's 1, the 3 P's is 4, and we need 1 D orbital to make the 5th bond. Last, something weird, xenon, a noble gas is bonding. Now, I would not ask you at this point to put this structure together. Okay? I would give it to you. Okay? In grade 12 AP, you'd have to learn how to put this together. But you just do the steps. You take all the valence electrons, okay, assign them from the outside, and work your way to the middle. So it wouldn't be that hard to do. Okay? Xenon is way down in our 5th period, so there are empty d orbitals that can be used to bond a noble gas with. When you count all the electrons, and get octets on the outside, which I'm not going to do, you're just going to have to trust me, you end up with 4 extra electrons that you assign to the middle. So xenon tetrafluoride has 2 lone pairs and 4 bonds on the fluorine. Okay, again, I'm not going to ask you to draw this. Next year you will. Okay. Again, it would come from counting the valence electrons on xenon, the 7 times 4 with the fluoride, octets on the outside going to the middle. No different. Okay. But I might ask you what the hybridization is of this. And the one thing to realize here is the lone pairs take up an orbital, so we have to count them. So there are 2 lone pairs and 4 bonds. So there's 6 total orbitals needed between the lone pairs and the bonds. So S is 1, the 3 P's is 4, the first D is 5, the second D is our 6. So we see the same hybridization as sulfur hexafluoride. And anything that has the same hybridization has the same shape. So when we get into shapes, if you realize the hybridization is the same, it has the same bond angles, it has the same 3-dimensional geometry. Okay. So that's our incomplete octet. Almost done. Okay. One last topic. It's a nice follow-up from this slide. We've got some atoms that have empty orbitals. We've got beryllium with 2 empty orbitals, boron with 1, and they can create coordinate covalent bonds. A lone pair can pop into, a lone pair from a different atom can pop into that orbital and form a bond. A bond is 2 electrons, but this is a bond from 2 and 0. Okay. This would be a nice friend to share with. You're going to share money. One's going to put in 0, one's going to put in $10, and you're going to share it. Okay? So it's not a 1 and 1 sharing, it's a 2 and 0 to make our shared covalent bond. Then there's going to be a reaction. One really common organic compound is ammonia. It's talked a lot about in Chem 30. It's really important for fertilizer. Ammonia is NH3, and it's got a lone pair. It bonds just like we expect from nitrogen all the time. Nitrogen has a lone pair and 3 singles. I just strategically align my lone pair and nitrogen, and then we've got our 3 bonds. Okay. Group 5, we expect 3 bonds. Nitrogen, phosphorus, 3 bonds is what's common. Okay. Now that lone pair can pop into an empty orbital, and I'm going to use boron. So my bond angles aren't perfect here. When you learn the next lesson, you can come back and complain about my bond angles. But I've strategically aligned stuff for the sake of my drawing. So we've got a lone pair of nitrogen, we've got an empty orbital on boron, and this can do a reaction. So I'm putting a plus. That's normally how we write reactions, this and that, this plus that. Okay? So this lone pair can form a bond. 2 and 0 instead of 1 and 1. And the whole thing comes together. Dash, I'm going to replace those 2 dots with a dash to the boron. And then boron has its octet. Nitrogen still has its octet, and everything's stable. So boron often has an incomplete octet, okay, but it can have it filled. Okay. There's 2 terms for this. A lot of textbooks will call it coordinate covalent bond. That's what I normally use in Chem 20. The AP textbook we're using calls it a dative or dative bond. Okay, I'll tend to stick to the coordinate covalent. Okay, but they're synonyms; they mean the same thing. So if a university professor uses either of these words, they mean a bond that's 2 and 0. Okay. So that wraps up all your Chem 20 skills for putting molecules together. Okay. Again, I'm being repetitive, but the main thing you're going to get assessed on is just using bonding capacity. So we haven't talked about that a lot lately, but that's where we started, and that's where you're going to put most of your time practicing. So I'm just going to end with a little bit of a flow chart to try to put this all together. So we've got bonding as a heading. And then we could get 2 different types of bonds. We could have covalent bonding, or we could have ionic. Okay? And with ionic, you're largely just needing to be able to draw Lewis dot diagrams for those ions, the square brackets. How would you tell which way? If you're asked to tell, you would look at change in electronegativity. Greater than 1.7, ionic. Less than 1.7 would predict covalent. Okay. Now, only use that prediction if you're asked to. Okay. So that's kind of the end of the ionic flow chart. Okay. If you're trying to figure out something that's covalent, your first default is to use bonding capacity. I'm just going to write BC. How many single electrons does it have? Okay. But if that is going to fail, you have an ion, or you have sulfur hexafluoride, and there's no way sulfur with bonding capacity could bond with 6Fs. Okay. You're going to use the 5 steps in the previous lesson. Okay. Count the valence electrons, connect everything to the central atom, octets on the outside, work your way in. Okay. And then you've got formal charge and resonance is kind of separate tiny little pieces under the 5 steps. Resonance could show up under bonding capacity. We wouldn't go there. Okay. So this is how you want to tackle problems. You're going to get maybe 5% ionic because you're just drawing those Lewis symbols. Okay. You're going to get maybe 5% to 10% of your questions with the 5 steps with the ions. Okay. You know, so 85 to 90% is going to be bonding capacity. So I've really biased you. I've spent so much time on the 5 steps in formal charge and resonance, but it's not the heart of your exam. It's going to be like, you're going to get 1 question on formal charge, 1 question on resonance.